Welcome back. Today, we're diving into some really interesting research shaking up generative AI, specifically looking at diffusion transformers, or DIT.
That's right. These models are pushing the boundaries for speed and quality in image generation.
They are, but the sources we looked at identified, well, a pretty major bottleneck. It seems the whole system's performance is being held back by a component that hasn't really kept up.
Yeah, it's a bit of a hidden weakness, you could say. While the transformer part, the DIT itself, has evolved super fast, the foundation it's built on, the autoencoder creating the latent space,
Still using older tech?
pretty much. We're talking about
Yeah.
the standard variational autoencoder, the VAE, often called the SDVAE in stable diffusion contexts.
Okay, the SDVAE. So if that's the bottleneck, what exactly are the limitations? Why are we calling it, legacy?
Well, the research points to three main things. First, it relies on older convolutional backbones. They're just not that efficient anymore.
Right.
Second, it's really aggressive about compression. It forces the image data into this tiny latent space, like only 4 dimensions.
Wow, 4. That doesn't sound like much room for detail.
It really isn't. And maybe most importantly, it's trained almost entirely for just pixel-level reconstruction, just making the output look like the input.
So it's not really learning the meaning of the image, just how to copy it.
Kind of. This focus on pure reconstruction means the representations it creates are, well, weak. They don't give the DIT model built on top the best possible starting point.
Okay, so the foundation is shaky. The mission for this deep dive, then, is to explore what this research proposes instead. A pretty radical shift, it sounds like.
It really is. The core idea is swapping out that VAE for something new, the Representation Autoencoder, or RAE.
RAE, okay, what makes it different?
It flips the whole autoencoder philosophy. Instead of learning representations from scratch while trying to reconstruct, the RAE leverages all the progress in self-supervised visual learning.
So using models that are already trained to understand images.
Exactly. It takes a powerful pre-trained encoder like DINO or SigLIP or MAE, models known for strong semantic features, and it freezes it, doesn't train it further.
Freezes it. Okay.
Then it only trains a decoder. The decoder's job is just to learn how to map those rich existing features back into an image.
That definitely goes against the grain.
Right.
I mean, the old thinking was that these semantic encoders, because they focus on high-level stuff, objects and concepts,
Would be bad at reconstruction, right?
yeah, they'd only capture the gist, maybe give you blurry or abstract outputs, not sharp details.
Well, it turns out that assumption was wrong. The research shows the RAE actually does better on reconstruction quality compared to the standard SDVAE.
Better? How much better? Do we have metrics on that?
We do. They use RFID reconstruction Frischet inception distance. Lower is better means the reconstruction is closer to the original.
Yeah, the numbers.
An RAE, using an MAEB encoder, gets an RFID of 0.16. The SDVAE, it scores 0.62.
0.16 versus 0.62. That's
Big.
quite a gap, almost 4 times better fidelity.
It's a huge improvement in just pure reconstruction. Less blurry, less artifacty images.
Okay, impressive on its own. But you said the RAE uses encoders known for semantic strength. Does that carry over?
That's the real kicker. It inherits that strength. We can measure this using linear probing accuracy, basically, how easily a simple linear model can classify images based on their latent codes.
And how does the RAE stack up there?
The SDVAE, remember, it's trained for reconstruction. It only gets about 8% accuracy on this kind of semantic dust.
8%, okay.
The RAE, using, say, a DINO V2B backbone, it keeps the high accuracy of that original encoder. We're talking 84.5% top 1 accuracy.
84.5.
Yeah.
Compared to 8. That's night and day. It means the RAE's latent space isn't just compressed pixels, it's actually organized by meaning.
It provides a much richer, more structured space for the diffusion model to work in, and there's another benefit too.
Let me guess, efficiency.
You got it. The SDVAE is computationally heavier. The sources mentioned it takes about 6 times more GFLOPs, that's compute operations for its encoder, and 3 times more for its decoder compared to an RAE for a standard 256 by 256 image.
So, better reconstruction, vastly better semantic understanding, and it's cheaper to run. Seems like a clear win.
It addresses the bottleneck for sure, but it introduces a completely new challenge for the DIT part of the system.
Okay. What's the catch?
The dimensionality. We went from that tiny 4-dimensional space of the SDVAE to, well, something like DINO V2B features, which are 768 dimensional.
768, that's a massive jump. So the diffusion transformer is now operating in this huge space.
And standard DITs just weren't designed for that. They were optimized for those low-dimensional VAE inputs. When you feed them these high-dimensional RAE latents, they break.
Break how?
Well, smaller models like DITs, they just fail to converge. They can't learn. Even big models like DITXL really struggle and underperform compared to how they do with VAE inputs.
Okay, so fixing the foundation created a problem upstairs in the transformer. How did the researchers solve that? It sounds like they needed some new tricks.
They did. They came up with 3 key solutions to sort of tame the DIT in this new high-dimensional world.
All right, let's break those down. What's the first one?
The first is about the DIT model's architecture itself, specifically its width. They found that for training to work reliably, the model's internal width, let's call it $, must be at least as large as the dimension of the RAE tokens, let's call that another $.
So if the RAE feature is 768 dimensions, the DIT with $doll has to be 768 or more. Why? Couldn't you assume the important information lives on some smaller intrinsic manifold within that space?
That's often the assumption, yeah. But diffusion models add noise, right? Gaussian noise. And this noise isn't confined to the hypothetical neat little manifold.
Ah, it pushes the data points off the manifold into the wider space.
Exactly. But the noise effectively makes the data distribution fill up much more of that high-dimensional room, the full 768 dimensions in our example.
So the DIT needs enough width, enough capacity to handle data points across that entire noise-expanded space, not just the original clean data structure.
Precisely. If dollars is less than nuller, the model just doesn't have the representational power. They even showed this in a simple toy experiment. Convergence only happened when a dello n and botter dollar.
Okay, that makes sense. A demanding requirement, though. It forces you to use wider, potentially more expensive models. What was the second fix?
The second fix targets the noise schedule itself, how noise is added over time during the diffusion process.
What was wrong with the old schedules?
They were mostly designed thinking about inputs like raw pixels, 3 channels, or the VAE latents, 4 channels, low channel depth. They scaled based on spatial resolution, but didn't really account for the depth, the channel dimension.
But now with RAE, the channels are the 768 feature dimensions.
Right. So when you apply Gaussian noise across both spatial locations and all 768 channels, the total effective dimensionality the noise is spread across is much, much higher.
Meaning the standard noise levels felt too small relative to the data space.
Essentially, yes. The signal-to-noise ratio was off. They found they needed a dimension-dependent shift in the noise schedule. They introduced a scaling factor, alpha, based on the ratio of the total effective data dimension and the token dimension.
And making that adjustment helped.
Dramatically. Just applying this corrected noise scaling in one experiment dropped the generation FID, the GFID, measuring image quality from a poor 23.08 down to 4.81, a massive improvement in stability and quality.
Wow, just from tuning the noise correctly for the dimensionality. Okay, what's the third solution? You mentioned noise-augmented decoding?
Yeah, this one tackles a subtle but important mismatch. Think about how the RAE decoder is trained.
It's trained on clean latent vectors, right? Yeah. The ones directly from the frozen encoder processing real images.
Exactly. Clean, discrete latent points. But what does the diffusion model produce at the end of its generation process?
It's been denoising step by step. So the final latent vector isn't perfectly clean. It's slightly noisy, maybe continuous.
That's the issue. The decoder is trained on perfect, clean points, but it's being asked to decode slightly noisy, continuous points coming out of the DIT. This mismatch hurts generation quality.
So the decoder isn't quite sure how to interpret the DIT's output.
Right. The fix is surprisingly simple. During the RAE decoder training, they add a little bit of Gaussian noise to the clean latents before feeding them to the decoder.
So you train the decoder with noise to make it robust to the noise it will see later from the diffusion process.
That's the idea. It forces the decoder to generalize better to the continuous, slightly imperfect outputs of the DIT.
Okay, but wait. Earlier we celebrated the RAE's amazing reconstruction quality, the low RFID. Doesn't adding noise during decoder training make the reconstruction slightly worse?
It does. There's a small trade-off. The RFID might go up a tiny bit, meaning reconstruction isn't quite as perfect.
So why do it? Why accept worse reconstruction for better generation?
Because the impact on generation quality, GFID, is much more significant than the small hit to reconstruction quality, RFID. The diffusion model really benefits from a decoder that smoothly handles its continuous outputs. It seems maximizing the final image generation quality sometimes means accepting a slight compromise on pure, noise-free reconstruction fidelity. It's a pragmatic choice.
Makes sense. So these three things, matching with dollar to dollar dollar, dimension-aware noise scheduling, and noise-augmented decoding together, they allow DIT to work effectively with these high-dimensional RAE latents.
They get it working well, but that first requirement, making the DIT with dollar match the latent dimension at dollar, that can get computationally very expensive, especially as node grows. Training transformers scales quadratically with width.
Right, making the whole model wider gets costly fast. They find a way around that.
They did with another architectural innovation called DTDH, that's Diffusion Transformer with a DDT head.
DDT head was that too.
It's a clever efficiency move. Instead of making the entire deep transformer backbone wide enough to match non-dollars, they keep the main backbone relatively standard. Then they add a specialized head, this DDT head, which is very shallow, only a few layers, but very wide.
Ah, so only the final denoising part of the network needs to have that massive with Delo GL dollar.
That's the idea. It confines the high-dimensional processing to a much smaller, shallower part of the network. This lets them meet the width requirement without paying the full quadratic cost across the entire deep backbone.
How much more efficient is it?
Significantly, a DT-DHB model, for example, needs only about 40% of the training compute, the FLOPs, compared to a standard DiTXL that's wide all the way through. And despite being cheaper to train,
It performs better.
it actually outperforms the bigger, more expensive DiTXL in their tests.
That's a really neat architectural trick. But does it depend on the RAE?
Critically so. The research shows DTH provides little benefit or even performs worse if you train it on the old low-dimensional SDVAE latents. And they even tried training DiTDH directly on raw pixels, just making sure the token dimension matched the RAE's 768. Still performed much worse than using RAE latents.
So it's not just about having a wide head. It's the combination of the wide head and the rich, structured, high-dimensional input from the RAE that makes it work so well.
It seems the RAE provides the kind of representation that the DiTDH architecture can really leverage effectively.
So putting it all together, the RAE foundation, the fixes for high DAT training, and this efficient DTDH architecture, what does this mean for overall performance and speed?
The gains are pretty staggering. They report achieving convergence much, much faster, something like a 47x training speedup compared to models like SciTXL and 16x faster than RePXL.
47 times faster. That completely changes the economics of training these large models.
It really does, and the final quality is state-of-the-art. Using an RAE with the DiTDH XL model on ImageNet at 256 by 256 resolution, they achieved an FID score of 1.51 without guidance.
Which is already very good, and with guidance.
With auto guidance, they hit 1.13 FID. That's extremely competitive, very close to the theoretical minimum. Lower FID means the generated images are closer in distribution to real images.
1.13 FID is top tier. Does this scale well to higher resolutions too, like 512 by 512?
Yes, and efficiently. Because the RAE decouples the encoder and decoder, they can handle upsampling mainly in the decoder. By adjusting the patch size the decoder works with relative to the encoder, they can generate 512 by 512 images using the same number of latent tokens as they used for 256 by 256.
So the DIT doesn't need to process 4 times as many tokens. The decoder does the heavy lifting for resolution increase.
Pretty much. This approach is about 4 times more efficient computationally than just naively quadrupling the token count for the higher resolution, and still achieves excellent generation quality. They report 1.13 FID at 52 by 5212 with guidance after 400 epochs.
Okay, so let's try to synthesize this. The big shift seems to be rethinking the autoencoder, moving away from just seeing it as a tool for compression.
And towards seeing it as a way to establish a strong representational foundation. Using pre-trained encoders via the RAE gives you semantics and efficiency VADs lacked.
But that forced adapting the DIT, needing wider models because noise expands the effective dimension, needing dimension-aware noise schedules, and needing noise-augmented decoding for the continuous diffusion output.
Right. And the DDTDH architecture emerged as an efficient way to meet that width requirement without blowing up the compute budget.
It really reframes the whole pipeline, which leads to a final thought for you, the listener, based on this research.
Yeah, consider this. The work strongly suggests that the encoder, the part that creates the latent space, doesn't actually need to be learned specifically for compression. or even learned at the same time as the decoder or the diffusion model.
You can just take a powerful off-the-shelf vision model trained for representation learning.
Freeze it, and build the rest of the generative system around that fixed high-quality representation. It implies a future where we might decouple representation learning entirely from generative model training, sourcing the best possible semantic understanding from specialized models. It's a fundamental shift in how we might build these systems going forward.